Howdy! This is your friendly neighborhood physics teacher here, and we're going to go over some free body diagrams. What does balanced and unbalanced mean? Just to make sure I had a lot of questions about this, and I just want to make sure y'all do understand this to the best of your ability. So, first thing we're going to talk about balanced and unbalanced because that kind of leads into free body diagrams, and then from free body diagrams we will branch into kind of using equations, which is going into your second your Newton's second law. So we're going to talk about a little bit of Newton's second law here. This is just I guess help video over everything you've kind of gone over since I've been gone. So add second law to the to the title there. But okay, let's talk about what the difference between balanced and unbalanced is. Okay, so another way you can say equilibrium or unequilibrium, but I can spell balanced. So we're going to use balanced. Well, maybe I can spell balanced. Let's try that again. So if a system is balanced, and what I mean by system is an object with forces, object or objects, mainly just one object, with forces acting on it. So if an object is balanced, key thing, when you see the word balanced or at equilibrium, a couple of things need to pop in your head. So that means that your net force, now remember, net force is all the forces added up together. You might also see it like that. Those means the same thing. Net force, sum of the forces, all that means the same thing. So net force. So all those mean the same thing. So if it's balanced, all of those equal 0. So your net force, your sum of the forces equal 0. That means all the forces are balanced. Everything going left. So kind of key thing. All forces pointing left equal all forces pointing right, or pretty much same thing, little statement, all forces pointing up equal all forces pointing down. So that's basically what that means. Now, what that would look like in a free body diagram, so you have an object, oops, I'll try that again, hard to draw a straight line, pretend like the line's connected. So that means the arrow that's pointing down, which in that case would be force of gravity. Force of gravity always points down, equals the force of normal. In this case, since it's sitting on the table or ground or sitting on something, there's your force of normal. So the forces, the sum of the forces in the y direction, the force of normal equals your force of gravity. This one's pointing up and one's pointing down. With your forces in the left and right, it doesn't matter which one's which. We'll just make this force applied. We'll make this force friction. So that means your net force in the x direction, which is horizontal. That means your force applied equals your force of friction. That's all that's meaning. So your net forces are balanced. Now, since your net forces are balanced, that also means that there's no acceleration. No, I can't spell acceleration all of a sudden. Imagine that. Okay, I'm going to pretend like that says acceleration. That means there's no acceleration. So if there's no acceleration, we have two options. The object is either not moving or it's moving at constant velocity. So the object is either not moving or moving at constant velocity. So going back to our little free body diagram up here. So obviously, in the y direction, because of what we have drawn here, it's a box sitting on the floor. In the y direction, we can logically comprehend that it's not moving. We can logically comprehend that it's not moving in the y direction. It's a box sitting on the ground. Now, if it's moving in the x direction, we don't know. We don't know if it's moving or not moving in the x direction without other information. And that's when reading the problem, and you're, dealing with AP physics, reading the problem comes into play. So we don't have enough information to know if it's moving or not moving. And so if there's a free body like a free response question and asks you what's this box doing, you can logically say it's not moving in the y direction, but in the x direction, it could not be moving, or it could be moving at constant velocity because net forces are balanced, so there's no acceleration. That would be an appropriate answer for that, because you don't have enough information to say definitively if it's one or the other. Now, we know it's one or the other, because no acceleration means it's either not moving, not moving, or it's moving at constant velocity. So that's what balanced means. So the net forces is equal to 0. Means all the forces pointing left equal all the forces pointing right. All the forces pointing up equal all the forces pointing down. So your net force in the y is just normal. This is just an example. This is not the end all be all, because we'll talk about more examples. So that's just one example. And so in this case, the net forces are balanced. Force of gravity equals your force of normal. Your forces in the x are balanced. Your force applied equals your force of friction. It also means because your net force is 0, that means that your acceleration equals 0 as well. Your acceleration equals 0 as well. because that it can either A, not be moving, or moving at constant velocity. Using constant context clues, we can say that in the y direction, it's not moving because it's a box sitting on something, table, floor. But in the x direction, we don't have enough information to know if it's either not moving or moving at constant velocity. It could be doing one or the other. Now, I am going to kind of sidetrack. So that's talking about balance. But I realize a question I had, and I want to sidetrack real quick. So looking at now, this what I drew here is a free body diagram. Now, you can. I tend to draw boxes just because they're quick and easy. You can draw circles, you can draw triangles, you can actually draw, like if it says on a car, you can actually draw a car. It doesn't matter. I tend to either stick with boxes or circles because they're quick for me, but you can draw any shape you want. It doesn't have to be a box. Now, what a free body diagram is. So a free body diagram. So free body diagram. What a free body diagram is a representation or a diagram of an object with all the forces, and it's one object. Key thing there is it's one object. We're not dealing with a series of objects, we're not dealing with multiple objects, we're dealing with one object. So one object and what forces are acting on that one object. Okay, so it shows the forces. Forces are vectors. Remember, vectors means it has a magnitude and direction. Magnitude is represented by the length of the arrow. So the longer the arrow, the bigger the magnitude. So the longer the arrow, the bigger the magnitude. Now remember, magnitude just means number. The smaller the arrow, the smaller the number, or smaller the magnitude. That is a number sign, not a hashtag. So the length of your arrow matter. If you know one force is stronger than the other, draw it out. You don't have to sit there and get a ruler and do proportion or anything. Just make it obvious when I look at it, or when your AP graders look at it, they can see that one's way longer than the other one. If they need to be equal, like in this case, over here, your force of normal, force of gravity. I mean, yes, if you sit there and got a ruler, one would probably be slightly, especially with the force applied, force of friction. Maybe your force of friction is slightly smaller than force applied if I sit there and scrutinize it, but at first glance, they look like to be the same. And that's acceptable. But if one needs to be longer, you need to obviously draw one longer. The arrow part, where it points, just telling the direction the force is going. So, gravity always points down. So force of gravity should always be pointing down. Your force of normal is always perpendicular to the surface. So since the surface is like this, perpendicular means 90 degrees, right? So your force of normal always points perpendicular to the surface. And since, again, we have a box sitting on the ground, that force of gravity is trying to pull the box through the ground, but that ground's overpowering the force of gravity, so they should be balanced. The ground is preventing, or the table is preventing the box from going through the table. So the forces are balanced. Now, so there we go. Now let's talk about unbalanced forces. So that's what we're dealing with most of the time is unbalanced forces. So unbalanced forces Wrong color. Try to keep it consistent. Means you have a net force. So your net force is some type of number. So you have a net force. So since you have a net force, that means you have an acceleration. You have an acceleration. That's basically it. Now, what a free body diagram would look like in this case, this is just an example. We're going to show both examples. So we do have your force of gravity, force of normal, force applied, and force of friction. So your net force in the y would still be balanced. Your normal force equals your force of gravity. That's still not moving. It's not moving in the y direction. But in the x direction, it's not balanced anymore. Oops. Here's some of the forces. In the x direction, we end up equaling your force applied plus a negative force of friction. Now, it honestly doesn't matter which one you make positive, which one you make negative, and stuff like that. But we tend to make up, positive, down, negative, right, positive, left, negative. That has not changed. That has been consistent since we started physics, so we're just going to stick with it. And you can do the same thing with this equation over here. Your net force in the y direction equals your force of normal plus your negative force of gravity. But since it's balanced, you have zero net force, which that leads to saying that your force of gravity equals your force of normal. Because all I did was bring it over. With this, we're here on our force, our net force in the x. We're kind of stuck until we actually plug in numbers. So that's what I was saying. Your force is a vector. You need a number, which is represented by your variable here, and you need a direction. So it's either a negative or a positive. You could sit here and put positives here if you wanted to. To represent positive, negatives. I tend to drop the positive. I tend to just put the negative because a +4 and a 4 is the same thing. But whatever helps get you understanding there. So a few more examples. So you're going to tell me what's happening. Well, you're going to think what's happening and you'll hear me explain it, I guess. So another example. So a ball falling in the air. Ball's just falling. So what force is always there? Hopefully you said force of gravity. So force of gravity should always be present. Now, a ball falling through the air, you could just leave it like this, or you could argue that, not really argue, state that there might be a little bit of air resistance. Should say force of air. Now, are these vectors the same size? Hopefully you said no. So we have a net force in the y equals a force of air plus a negative force of gravity. And since we know force of gravity is going to be bigger because of the way we drew it, we know that our net force is going to end up being negative. Because it's going to end up moving down. So, ball is accelerating down. Now, in the x direction, so this is in the y direction. So in the x direction, we know that our net force in the x direction is equal to 0. We know that it's because there's no forces in the x direction. Oh, tilt back. Thank you. We know there's no forces. But remember, we have two options when there's no forces. So when there's no forces, well, we know the ball is not accelerating left or right. But what we don't know, so this could be an either or situation again. It can either be not moving or moving at constant velocity. Just because there's no forces represented doesn't mean the ball is still not moving. We just know it's not accelerating. So it could be not moving or moving at constant velocity. We don't know. And that's what throws a lot of people off. They think that there's no forces, that means obviously it's not moving. No, it just means it's not accelerating. So that's balanced forces or unbalanced forces. So that means in whichever x or y direction, the forces are not balanced. One's bigger than the other. So that means you have an acceleration in one of those directions. Oh, and I didn't talk about, so going back to our first example, since our force applied is bigger, that we know that our net force in the x is going to be positive because it's moving in the positive direction. So that's balanced forces and unbalanced forces. And a quick overview about free body diagrams. Now, I'll do a few more examples of free body diagrams. And kind of give you some hints about your free body diagram homework. I know I need to glance through a few more of those that have gotten turned in. Don't forget you have 2 trials and everything, so if you want to backtrack, please do. I want y'all to succeed. But okay, so let's do a few more just examples in general. So if you have okay, this is a couple of things that I know I had a couple of few more questions over with free body diagrams. So if you have a car that's slowing down, okay? So we're going to do a car slowing down. So again, I'm not drawing a car, I'm just drawing a box. But that is our car slowing down. Okay? Force of gravity is always there. Always points down. Our force of normal, because since the wheels of the car, now yes, you could sit there and be like, well, shouldn't there be like 4 forces of normal? Because we're treating it as one object. So that's why another reason why you just draw a box instead of a car. So yes, there's 4 points of contact on the car. So you could say that there's 4 forces of normal on each. That gets too complicated. So there's just one force of normal. And cars normally don't float. They're trying. They're getting there to try to get them to hover, but your force of gravity and your force of normal. So your net force in the y direction would equal to 0. And so when you do your net force, it'd be your force of normal plus a negative force of gravity. It's negative because gravity points down. We already know that your net force is 0. So we can bring our force of gravity over. And we get that our force of gravity equals to our force of normal. So since they're equal, we know they're balanced. So we know they're balanced. We already know that our net force is 0. And so we know that our acceleration is 0. What we possibly don't know if it's moving at constant velocity or not moving. Common sense, since a car doesn't move up and down, we know it's not moving in the y direction. Okay, so we can get all that information from that. In the x direction, if it's slowing down, what force makes an object slow down? So hopefully you said force of friction. So this is basically you've taken your foot off the accelerator and you're putting your foot on the brake. You're slowing down. There is no force applied. Now force of friction always goes against the motion. So the car is moving. So the car is moving to the right, or you can make it move to the left, doesn't matter. But the car is moving in one direction, so the force of friction would be going in the opposite direction. So this would be your free body diagram. So dealing with our net force in the x, it's not balanced because we only have one force. So that means our net force in the x equals a negative force of friction. So we know it's unbalanced. That means we do have a net force. In this case, it's a negative net force. So that means we do have an acceleration. So we know that the object is moving and we know it's accelerating. Now, how do we find these numbers? It's where Newton's second law comes into play. Okay. So that is the difference between balanced and unbalanced forces. I'll stop the video here. Hopefully that helps. I'll make another video over Newton's second law, and hopefully that answered a few of your questions. If you have any more questions, because I am responding very slowly, ask Miss Casanova or Miss Verona. They're in the Shoemaker building over at CTC. I know that helps my B-Day students, not necessarily my A-Day students. They will be added to the Schoology. So you could go to members and look through and message them on Schoology also. And so for B-Days, their tutoring is during B-Lunch. And I believe Miss Casanova's in the lab. So that's 106, I believe is that number. And then Miss Verona is in 102 over there. I believe, don't quote me on those room numbers. But my A-Day students, you can definitely message them on Schoology, and they will respond also. But I hope y'all have a wonderful day. Remember, you're loved and appreciated. Bye.